So today, we're going to go full-on forensic scientist to figure out how to read that soil and uncover its unique atomic fingerprint. Let's dive in.
So here's the game plan. First, we'll cover why you should even care about this stuff. Then, we're going to hunt for some tiny but super important ingredients. After that, we'll get our hands a little dirty with some lab prep, introduce you to our high-tech detective, and finally, we'll crack the code and figure out what all the data really means.
All right, let's zoom out and start with the big picture. I mean, think about it. Everything you eat, whether it's an apple or a piece of toast, it all starts in the soil. But here's the thing, the quality of that soil, it's way more than just dirt and water. It's actually more like a really precise chemical cocktail. If you have too little of one key ingredient, boom, the crop fails. But if you have too much, well, that can be just as bad, even toxic. So the health of our food it's directly linked to the health of our soil. And that's exactly why we need to know what's in there, down to the last atom. And that brings us right to our micronutrient hunt. Now, we're on the lookout for elements that plants need in ridiculously small amounts. But don't let the size fool you. They are absolutely vital for their survival and for our nutrition too. Yeah, think of elements like zinc, iron, copper, and manganese as, well, they're basically vitamins for plants. Plants don't need a ton of them, but if they're missing, oh boy, things go wrong fast. And just to give you an idea, zinc is actually one of the most common deficiencies you'll find in soils pretty much anywhere in the world. Okay, so how in the world do you find these tiny microscopic traces? Well, we use this absolutely brilliant piece of tech called an atomic absorption spectrophotometer. I know, it's a total mouthful, right? So we're just gonna call it the AAS. This thing is our high-tech detective, and it's amazing at finding just one specific element hiding in a super complex mix. So how does this detective do its job? Well, in a nutshell, it shines a really, really specific kind of light through our sample. A good way to think about it is like an atomic fingerprint machine. It's programmed to look for the unique signature of just one element and one element only at a time.
Okay, here's the science behind it, and it's actually pretty cool. Every single element has a favorite color of light, a very specific wavelength that it just loves to absorb. So iron will absorb light at a totally different wavelength than zinc does. And the AAS machine, it uses this fact to its advantage. It's kind of like having a key that will only, and I mean only, fit one specific atomic lock. But hold on. Before our fancy machine can work its magic, we've got to get the sample ready. I mean, you can't just shove a clump of dirt into a machine that costs millions of dollars, right? We have to carefully pull out or extract the micronutrients we're trying to measure. So let's walk through how that's done.
This whole process has a name. It's a standard operating procedure, or SOP. And it is all about precision. So first, you weigh out a super precise amount of soil. Then you add this special chemical solution called DTPA. What it does is it basically grabs onto the micronutrients we're looking for. Then you shake it. And I mean, you shake it a lot. And finally, you filter the whole thing to get a nice, clean liquid sample. And listen, when I say precise, I am not kidding. The procedure calls for exactly 10 grams of soil. Not 9.9, not 10.1, 10. Every single step is standardized like this so that the results from a lab in one country can be accurately compared to results from a lab halfway across the world. Okay, so to that 10 grams of soil, we add exactly 20 milliliters of that DTPA extracting solution. This ratio is so important. 1 part soil to 2 part solution. It's gonna be absolutely critical when we get to the final calculation later on. All right, then comes the shaking. The sample gets put on a shaker and agitated for a full 2 hours. And no, this isn't just for kicks. This is to make sure that the DTPA solution gets enough time and contact with the soil to really pull those micronutrients, which are bound pretty tightly to the soil particles, out and into the liquid. So, after you filter out all the gunk, the bits of dirt and clay and sand, what you're left with is this perfectly clear liquid. It's called a filtrate. And I know it might not look like much, but hiding in there, totally invisible, are the zinc, iron, and all the other elements we've been hunting for. And now it's ready for the AIS machine. Okay, great, our sample is ready to go. But how does the machine actually know what it's looking at? I mean, it can measure how much light gets absorbed, sure, but it can't just magically spit out a number like parts per million. We actually have to teach it first.
We have to build it a ruler.
And this right here, this is probably the most critical step of the whole process. It's called building a calibration curve. So before we can even think about testing our unknown soil sample, we have to run a series of standard samples. These are samples where we know the exact concentration of the element we're looking for. This is what gives the machine its reference points. So, for example, we'd run a standard that we know has 0.5 milligrams per liter of zinc in it, and we write down the machine's absorbance reading. And we do it again with a 1.0 standard, then 2.0, then 4.0. And you start to see this really clear pattern emerge. The higher the concentration of the element, the more light it absorbs. Makes sense, right? Then what we do is we plot these points on a graph. We put concentration on one axis and the machine's absorbance reading on the other. And if we've done everything perfectly, we should get this beautiful straight line. This line, this is our ruler. This is the key that lets us turn any random absorbance reading from our soil sample into an actual, precise concentration. All right, this is it, the moment of truth. We've got our prepared soil sample, we've got our perfectly calibrated machine with its shiny new ruler. It is time to finally decode the data and get our answer. So we take our clear filtrate and feed it into the AAS. The machine does its thing and spits out one single number, the absorbance reading. Now we just take that number, find it on the vertical axis of our graph, we go across until we hit our line, and then we drop straight down to the horizontal axis. And just like that, the graph tells us the exact concentration of the micronutrient that was in our liquid sample. We are so close. That number we just got from the curve, let's just call it C for concentration. That's the concentration in the liquid, but we want to know what it was in the original soil, right? So we just do one last simple calculation. We take that number, C, and we multiply it by a dilution factor of 2. Why 2? Because remember way back when we used 10 grams of soil and 20 milliliters of liquid? That's our 1-to-2 ratio coming back into play. And there you have it, the final result. So for this particular sample, we might find out that we have 0.7 milligrams of zinc for every kilogram of soil. We then compare that number to the official critical limits, and what do you know? It falls into the low category. On the other hand, our iron content came in at 5.2, which puts it right in the sweet spot, the medium or optimal range. So you see, this entire kind of complex process, it all boils down to a single incredibly useful number. A farmer can now look at this and say, okay, my soil is definitely low in zinc, and they can apply exactly the right kind of fertilizer to fix it. There's no more guesswork, it's just precise, data-driven decisions. And that means healthier crops and, at the end of the day, more nutritious food for all of us.